Hi everyone! Welcome to part 3 of chapter 16. Today we're going to continue our talk on acids and bases. Last time we left off, we talked about how to calculate the pH of a strong acid. Today we're going to look at how to calculate the pH of a weak acid, which is really different from calculating the pH of a strong acid. And then we're going to talk about how to calculate the pH of a strong base and of a weak base. Spoiler alert, calculating the pH of a strong acid and a strong base are really similar, and calculating the pH of a weak acid and a weak base are really similar. Strong acids and strong bases don't form an equilibrium, whereas weak acids and weak bases do. So that's what we're going to talk about today. So last time we talked about strong acids, and we said that strong acids completely dissociate in water. Well, weak acids don't dissociate in water. That's what makes them a weak acid. When we're talking about strong versus weak, we're looking at the percent to which they dissociate in water. So weak acids will donate only a small fraction of their H+ ions. So they predominantly float around in solution as the molecule that you put them in, as the weak acid molecule. Whereas when we looked at the strong acid, right, it completely dissociated. Like hydrochloric acid completely split into H+ and Cl-. Well, if we look at HF in this image, right, if we put hydrofluoric acid in, most of the hydrofluoric acid molecules will stay together, and only a small fraction of them will break apart. Okay, so that's how we're going to distinguish between a strong acid and a weak acid. Weak acids are less than 5% ionized in water. Oftentimes, they are much, much less than that. They're maybe 1% or less, right? So the concentration of H3O+ that's floating around solution is much less than the concentration of our weak acid. Okay, and so as you can see here, we're going to have both weak acid and hydronium, right, H3O+, and the conjugate base, which is F-, floating around in solution, which means we are going to have an equilibrium. Okay, so weak acids are assumed to dissociate slightly, like I said, less than 5%. So before dissociation, we have completely our weak acid. We just dump in weak acid, and then our weak acid, right, some of those weak acid molecules will interact and react with the water. And so a small portion of them will form H+, or, you can think of this, like I said, as H3O+, and then the conjugate base A-. So again, after dissociation, we're still going to have a bunch of our weak acid, but we're also going to have some of our hydronium ion and our conjugate base. So this means that we are going to have a very small Ka, right? At equilibrium, most of our weak acid is still weak acid. It made very little, product in this case, right? Our very little hydronium and conjugate base. So we would say that this is reactant favored. Whereas when we were looking at our strong acids had a very large Ka, right? We said that they're so large that, usually we don't even bother to measure them because it doesn't matter. We assume that they completely dissociate. And so strong acids would be product favored. Okay, so our acid ionization constant Ka that we keep talking about is our way of measuring the strength of the acid. Okay, so if it has a very large Ka, it's going to completely dissociate and, will completely break into the, hydronium ion and the conjugate base. If it has a very, very small ionization constant, a very small Ka, then most of it will exist as our weak acid. Okay, so again, the larger our Ka value, the stronger our acid will be. And when we get into this, the larger your Ka, the stronger your acid, the lower the pH. Okay, and so that's a really easy way to, check your work, make sure you're doing things right. So our Ka expression here, we're always going to have our hydronium ion concentration times our conjugate base, which is A-, over our acid. Okay, again, you'll notice that we don't include water in these equilibrium expressions because water is a pure liquid and therefore its concentration isn't going to change, right? We don't really report the concentration of water in water. That'd be a little bit silly. And either way that you want to write the reactions are fine. So I've shown it both ways. So here we have water and here we have without water. And so you're going to either get, hydronium or you're going to get the proton. Either way is fine. Whatever way you like better, write it that way. And you'll notice I actually switch between it when I'm writing it and, in the lecture worksheet, just based on which way I think will serve my purpose best, or, this is more of a shorthand way of writing it. So like I said, either way is fine, and you can switch it up if that makes you happy too. But our Ka is going to then show up differently. You'll either see it written as hydronium or as H+. Just remember that those mean the same thing. So here's some examples of weak acids. We talked about hydrofluoric acid last time. It's one of our only binary acids, right? Our only one with a hydrogen and a halogen that's a weak acid. And we've got acetic acid, and then we've got these acids on the right. You'll see they say diprotic or triprotic. And what that means is that diprotic tells you there are two protons that are acidic, right? So these two hydrogens can both fall off. And the same thing here, right? These two hydrogens are both acidic. These three hydrogens are both acidic. And what that means, right, is that they won't release both of those hydrogens at once in a reaction. Like if we have sulfurous acid, it will react with water. And our first one will release one of the hydrogens. And then it can undergo another reaction with water, right? And we'll take that conjugate base from the previous reaction, we'll react it with water, and then we will get our final conjugate base. Okay, so they don't both happen at once. The first hydrogen is usually fairly easy to pull off. It's fairly acidic, right? When I say pull off, I mean, I'm talking about as an acid, right? So our first, the first hydrogen is fairly acidic. The second hydrogen tends to be slightly less acidic. And, in the case of phosphoric acid, that third hydrogen would be even less acidic. So normally if we are talking about an acid-base reaction with something that's diprotic or triprotic, we're usually just talking about pulling off one of the hydrogens, usually not both. So here's some more weak acids. There's a bunch of them, and you'll notice going from the weak acid to the conjugate base, all that we've done is we've removed a hydrogen and added on that negative charge, right? Because when we pull off that H+, it leaves our conjugate base with a negative charge. It's got some leftover electrons. And then you have these Ka values down the side. I want you to know that I will never ask you to memorize a Ka value. They will always be given to you. I would expect you to know, if I give you, I would expect you, to be able to write the formula of these acids, especially if they are a polyatomic that you should know, like you should know phosphoric acid, you should know sulfurous acid, hydrofluoric acid, but you wouldn't be expected to know something like citric acid. But given any of these formulas, I would expect you to be able to figure out what the conjugate base is, because all you're going to do is you're going to take off one hydrogen and put the negative onto the molecule. And the Ka values, like I said, I will always give to you. You will not be expected to memorize those. And remember, Ka values, right? The larger the Ka value, the stronger the acid. So up top, this iodic acid, this is our strongest weak acid in this particular list, whereas hydrocyanic acid is very weak. Because remember, that's telling you essentially how much it dissociates, right? So our iodic acid is going to dissociate a lot more than our hydrocyanic acid, meaning that iodic acid is much stronger. Here's some more. This is just a bunch of different ones, bunch of different ways to look at it. This table shows you the ionization reactions. So like for chlorous acid here, again, you're having chlorous acid, it's reacting with water, and it's going to form H3O+, and again, there's its conjugate base. You've got a bunch of Ka values there. And then the pKa we've talked about previously. Remember, pKa, the way that you're going to do that is you're going to take the negative log of the Ka. So to get from there to there, we take, negative log of 1.1 times 10 to the minus 2, and that will get us our pKa. So for a very strong acid, we want a very large Ka, and we want a very small pKa. I think of pKa as being related to pH. Okay, so like if we wanted something to be really acidic, we would want a very low pH. So our really acidic acids will have a very low pKa. And so that can help you remember that. Okay, we've got a practice problem. So for these, I want you to write the reactions of these weak acids with water, and then I want you to write the expression for the acid ionization constant. So that would be like our mass action expression when we were doing our equilibrium. So go ahead, pause here, write the reaction, and then our acid ionization constant. Okay, so here's our reaction for hydrofluoric acid with water. So again, hydrofluoric acid reacts with water. Our conjugate base would be F-, and that hydrogen has been transferred to the water, making it hydronium. And then for our expression, we've just got our conjugate base times our hydronium over our weak acid. Same thing with sulfurous acid. Sulfurous acid will react with water. And again, like I said, it's just going to donate that one hydrogen, not both of them, just one. And so then we get our our conjugate base and then our hydronium ion. And then there's your Ka expression. One just little tidbit here. When we have a strong acid, that's telling you that there's a very weak attraction between our hydrogen that's on there and our conjugate base, or the base piece. Okay, so there's a very weak attraction. And so that could be for two reasons. One, it could be due to a really large difference in electronegativities, or it could be due to a really big size difference. And we're going to get into this more a little bit later in this chapter. But what I want you to know here is that if you have a very strong acid, that's telling you there's a weak attraction between your hydrogen and your conjugate base. And if you have a weak acid, that means there's a very strong attraction between your hydrogen and your conjugate base, right? It's not going to fall apart in water, whereas in a strong acid, our hydrogen would be more attracted to the water molecule than it is to our conjugate base. So to sum it all up, a strong acid is a strong electrolyte. If you put your strong acid in water, pretty much all of it ionizes, right? It completely falls apart. That HA bond breaks apart and you're going to be left with A- and H3O+. Whereas a weak acid is a very weak electrolyte, meaning that most of the molecules will stay as your acid when they are floating around in solution, right? Very few of them will react with water to form A- and H3O+. And again, I talked about this last time, but the single-headed arrow, we use those for strong acids to indicate that pretty much all of them ionize and we are not really making an equilibrium. Whereas we will use a double-headed arrow with the weak acids because you will see that equilibrium there. Okay, so last time we talked about finding the pH of a strong acid, and we said that since strong acids completely dissociate, we can use our concentration of our strong acid as our concentration of H3O+, and we can just take the negative log of that, and we're done. Well, if you'll recall from that image, right, when we have a weak acid, we have some of our acid left, and we are going to have some H3O+, right? So we don't have this single-headed arrow where all of it ionizes. We only have partial ionization. Okay, so since we only have this partial ionization, we are going to have to solve an equilibrium problem, which means now we get to do more ice tables. So here's how you're going to go through this. So the first step will be to always write the dissociation of the acid in water, right? Just write your acid reacting with your water to produce hydronium and the conjugate base. Start there. And then you're going to make an ice table. And so you'll fill in your ice table with what you're given. Usually you're just going to be given the concentration of your weak acid to start and your Ka value. That would be really, really typical problem. And then keep in mind the stoichiometry of the reaction for that change line. Pretty much in this chapter, guys, it's always going to be 1, right? Because one of our acids is going to react with 1 water to make 1 H3O+ and 1 conjugate base. So that's easy for this chapter. Then you're going to set up the law of mass action and substitute the expressions for equilibrium concentrations into K, right? So that just means all of those X's and concentrations, you're going to plug that into our law of mass action. And then we are going to figure out our X value, right, which will be our H3O+, and then we'll use that to calculate the pH. And then make sure your answer makes sense. If you're calculating the pH of a weak acid, make sure it didn't come out as a basic pH. That would really clue you in that you've done something wrong. So just use logic at the end to make sure you've done it right. Okay, so here's an example problem. So this says, what is the pH of a 0.50 molar solution of acetic acid? And there's our Ka value. Okay, so the first thing we're always going to do is we're going to write the dissociation equation of the weak acid in water. So here's our acid. It reacts with water, forms our acetate ion and our hydronium. Next, we're going to do an ice table. So we'll bring back our reaction. We'll make an ice table. and then we are going to fill in what we know. So we know our initial concentration of our weak acid. So that will go there. And we're never going to write anything for water. So I always just kind of put an X here, just kind of cross that out so that I don't try and do anything with it. And then we don't have any of our conjugate base or our hydronium. So now we're going to go ahead and use our weak acid, right, to shift our reaction to the right. So we're going to get minus X plus X plus X. Nothing exciting so far. And then we're just going to, remember I plus C always equals E. So we're going to add straight down to get our values. So there you go, super straightforward on our ice table. Our next step is to use our law of mass action, substitute all of those equilibrium concentrations into that K expression. So I carried this forward from the previous page. There's our E line, and we are going to plug that into our Ka expression. So our Ka expression will be our products over our reactants, and we're just going to plug in our values. So we have Ka that was given in the problem up here. Okay, and it's going to equal X times X over 0.50 minus X. And so since Ka is very, very small, we can use our approximation here. So we're just going to get rid of this whole minus X business, and we'll have X squared over 0.50. When we're doing these weak acid problems, pretty much I will always give you ones where this approximation works. Okay, so you don't need to go through and check every time. I know that's a really good habit to get into, but if you see that this is times 10 to the minus 3, or or smaller, like minus 4, minus 5, sometimes it'll be like minus 10, right? If you see that, go ahead and just use the approximation in this chapter. Okay, so now we can figure out our concentration of H3O plus and the calculated value of X and pH and all the things. So here we go. We've got that from the previous page. So if we go ahead, we multiply both sides by 0.5, we take the square root, we will get that X is equal to 3.0 times 10 to the minus 3 molar. And since that's our concentration of H plus, or like I said, of H3O plus, either way, now we can figure out the pH. All we do is we take the negative log of that concentration, and that will give us our pH. And then again, like I said, double check. So 2.52, that's an acidic pH, and it's a weak acid, right? Acetic acid is a weak acid, so we're not getting something like 1 or 0.5, right? We're getting 2.5, which is a weak acid pH. So that tells us that it's likely we've done the problem correctly. Another way that we can measure the strength of an acid is to determine the percent of the acid molecules that ionize in the water. And so we call that percent ionization. And so the way that you're going to do this is you're going to take the concentration of your ionized acid over your initial concentration and multiply it by 100. The higher our percentage ionization, the stronger the acid. So like a strong acid, we say is going to ionize like 100%, right? Or like 99.99 kind of a thing. So if we have, a very high percent ionization, we're having a very strong acid. Usually these acids will, like I said, they will dissociate like 5% or less. So the way that we would do this on this last problem, if we were to look at that, we would take this concentration here. So we would make 3.0 times 10 to the minus 3 over 0.50 times 100. And that would get us our percent dissociation for this weak acid. Okay, so it's nothing exciting. Just if I ask for the percent ionization, then you're just going to do your hydrogen over your initial acid concentration times 100. Or if I ask for the pH, then you're just going to take the negative log of that hydrogen ion concentration. But again, just like before, we're pretty much always solving for X, just like we've done in the previous chapter. If you happen to have a mixture of acids, so there's two ways this can show up, right? If you have a strong acid and a weak acid, or you have a weak acid and a weak acid. Sometimes I'll give you strong acid and strong acid, so we'll talk about all three of those. But if you have a strong acid and a weak acid mixed up, don't even worry about the weak acid, because the weak acid is so weak compared to the strong acid that the concentration of H3O plus will be completely due to the strong acid. The weak acid will only make a small amount of H3O plus through that ionization with water, and it's not going to be enough to affect our pH. So if you have a mixture of a strong acid with a weak acid, you're just going to use that concentration of your strong acid to tell you the pH. If you have a mixture of weak acids, then you need to figure out which one of those is stronger. And typically what will happen in that case is one of them will be significantly stronger than the other, and you'll use that as your quote-unquote strong acid and calculate the pH from there. You'll still have to do that whole equilibrium calculation like we were just talking about, but again, only with the stronger one of the weak acids. You don't have to do it with both because one of them will have a negligible contribution of the hydronium ion compared to the other. If you have two strong acids, which I don't have on here, but if you have two strong acids, you will need to figure out the total moles of H3O plus that are being produced from each one, and then divide it by the total volume, right? And that will give you your concentration of H3O plus, and then you can take the negative log of that. So I'll just make a note here. If you have, two strong acids, you need to find your total moles of H3O plus over your total volume in liters, and that will give you your molarity of your H3O plus. And then you can take the negative log of that to find your concentration. All right, strong bases. So if you have a strong base, right, strong bases are going to essentially act like strong acids. They are going to completely dissociate in water. So like if you have sodium hydroxide, that means when you put it into water like this, it's going to break up completely into sodium and hydroxide. These are strong electrolytes, right? These are ionic compounds. They're usually pretty soluble, and so they'll break up fairly easily. Sometimes you'll have ones that are multi-OH, like calcium hydroxide, magnesium hydroxide, right? And they are going to completely dissociate in one step, which means that if I put calcium hydroxide into water, it's going to break up into calcium and 2 hydroxides. So pay attention to that when you're calculating pH, that you would need to, say that this was, 1 molar calcium hydroxide, you're going to end up with 2 molar hydroxide because it splits into 2 pieces. Okay, but they completely dissociate in one step, not like those diprotic and triprotic weak acids we were talking about before. This is a strong base. It will completely dissociate all at once. So for a generic base, we're going to use BOH. So this is something in our hydroxide. So it's going to break into that cation piece and hydroxide. They're always going to be metal hydroxides, right? They're going to use, pretty much the alkali metals or the alkaline earth metals. So the metals in group 1 or group 2 on the periodic table. The group 1 hydroxides are the most common because they're really soluble. So most times in lab, you'll see us use sodium hydroxide or potassium hydroxide because they're really easy to dissolve. Sometimes, though, we will use the group 2 hydroxides, so calcium, barium, magnesium, and strontium. They're just a little less soluble, and sometimes they'll react with other things, which can cause problems. But again, we do use them on occasion. Just know that all of those will be making, the 2 hydroxides rather than just the 1, like sodium and potassium. Regardless, though, the pH of these strong bases is going to be calculated directly from the concentration of the base in solution. So this is going to be just like how we were doing it for the strong acid. So like I said, if you have, 1 molar sodium hydroxide, that means you're going to have 1 molar hydroxide. But if you had 1 molar calcium hydroxide, right, CaOH2, then you're going to end up with 2 molar hydroxide. But either way, we can use that concentration of hydroxide to directly calculate the pH. No equilibrium necessary because, again, we're having this single-headed arrow. They're going to completely dissociate. We're not going to form an equilibrium. So here's a practice problem. Calculate the pH of a 0.25 molar solution of potassium hydroxide. I'd like you to try this out. So go ahead and pause here, try this problem, come back when you're ready. Okay, So we have this 0.250 molar solution of potassium hydroxide, and we are going to assume the potassium hydroxide completely dissociates in water. So that's giving us K plus and OH minus. So if we have 0.250 molar solution of potassium hydroxide, we know that we are going to have 0.250 molar solution of hydroxide. So we can use that directly as our concentration of hydroxide. And so we can find the POH, be careful there, right? Because this is hydroxide. We are finding the POH, not the pH. So when we take the negative log of our hydroxide concentration, we are getting, 0.602. And so if you had thought, say you did this on accident and you calculated the pH and you got this, your brain should be like, okay, well, that would not be the pH of a base, right? That is a very, very low pH. Something has gone wrong, right? And that's because you've calculated the POH because you took the negative log of the OH minus concentration. And the way that we shift that over to pH is we just do 14 minus that value, and that will get us pH. And then you would see, it's a very high pH. That makes more sense as a base. All right, so weak bases. Weak bases behave really similarly to weak acids. It's the same kind of thing where only a small fraction of our molecules will accept that hydrogen, right? Only a small amount of our molecules will ionize. Okay, so it's a very weak electrolyte. Most of them will still exist as the weak base. So like here, ammonia, when we put ammonia into water, most of them will still exist as ammonia, and only a very few of them will accept that hydrogen. So again, less than 5% ionization in water. Usually it's less than 1% or so. So our concentration of our hydroxide is much, much, much smaller than our concentration of our weak base. Most of our base will still exist as the weak base in solution. So here's a reaction, right? Here's our example. So if we have, this is called methylamine. So if methylamine reacts with water, we're getting this methylammonium and hydroxide, okay? It's always going to produce the conjugate acid and hydroxide. So we have base plus acid gives us conjugate acid plus our conjugate base, okay? And in this case, it's always, our conjugate base is always going to be our hydroxide. And now we are going to have Kb values instead of Ka values because this is a base dissociation constant. So here we have our Kb value is going to equal, again, our products over our reactants. Same stuff, right? We're still not going to include water because it's a pure liquid. So this is very similar, like I said, to the weak acid. Just now we are producing hydroxide in solution instead of a hydronium. So here's a generic reaction for our weak base reacting with water. So B, so this is just any base, reacts with water, and it's always going to form BH plus because it's always going to gain a hydrogen, right? It's going to accept that hydrogen, and then it's going to form hydroxide in solution. So our Kb values will always be our conjugate acid times our hydroxide over our base. And people tend to struggle a little more with this weak base. People are usually pretty good with writing the weak acids reactions because you're just going to take off a hydrogen. And for some reason, people struggle with it so much more when we are adding a hydrogen on. I'm not really sure, but all weak bases do this exact same thing. Don't try and make it hard. Just go with it. So here's some weak bases. And again, I wrote at the top that a lot of people struggle with this, and it's because it's true. But the way that you're going to recognize a weak base is you're going to look for the nitrogen. Do you see these all have this NH piece, right? All of them. They all have this nitrogen at the end. Okay, and so what's going to happen is that nitrogen, right? All of these nitrogens, that nitrogen is going to form 3 bonds, and then it has this lone pair. And the lone pair can accept that hydrogen, right? And so it's going to go find some H plus, and it's going to bond to it. Okay, so that's what's happening. So when you're trying to figure out a strong base versus a weak base, strong bases are always going to have that hydroxide on there, like sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. Whereas a weak base is always going to have a nitrogen on it to accept that hydrogen. Okay, and so when it does that, it's just going to add a hydrogen onto the end, and it's going to gain a positive charge because it's gaining that H plus. And again, we have these Kb values. The larger the Kb value, the stronger the weak base is. And, the smaller the Kb value, the weaker it is. Here's some more of them, just some more weak bases. The ionization reaction is written there. Again, we're always going to gain a hydrogen off of water. We're going to have our conjugate base, our conjugate acid and our hydroxide. So here's some more amines. This is what I was talking about previously. These are all nitrogens. So these are nitrogens, the blue ones. And then it's showing that lone pair. And that lone pair is where it can accept that hydrogen off of water and it can form the bond. So all of these amines, right, all of these nitrogens can do this exact same reaction. All right, let's go ahead and try a practice problem. Write the reaction for the weak bases with water, and then write our Kb expression. So go ahead, pause here, try this, and then come back when you're ready. Okay, so for this is methylamine, and so it's going to react with water. Again, it will gain a hydrogen off of water and form the hydroxide. Our Kb value will always be our products over our reactants, just like when we were doing Ka. And then the second one is going to react very similarly. Again, we are going to pull a hydrogen off of water, so it's going to go from a 2 to a 3+, and then we're getting that hydroxide as well. And again, products over reactants for our Kb value. So to sum up, a strong base is a really strong electrolyte. So practically all of those base molecules are going to form hydroxide ions by dissociating in water. So our base, and it's going to pull off this OH, and it's going to, float away. Our B plus our OH minus. So again, that's an ionic compound, going to completely dissociate in water. A weak base, though, very similar to a weak acid, is going to form an equilibrium with water, where only a small amount of those weak base molecules are able to pull a hydrogen off of water and form our conjugate acid and our hydroxide. So again, single-headed arrow with a strong base, double-headed arrow with a weak base. So we were just talking about this base ionization constant, Kb. Again, that's going to be a measure of how strong our base is. We don't bother writing it for our strong bases, just like we didn't bother writing it for our strong acids, because they are going to completely dissociate and we're not going to be left with any of our strong acid or our strong base at the end. But for our weak acids and weak bases, right, we are going to write that base ionization constant. In this case, it's our Kb value, so that we can find our pH, because it undergoes an equilibrium with water. All right, let's go through finding the pH of a weak base. Spoiler alert, it is the exact same thing we've done with a weak acid. The only thing that's going to be different here is that we are going to solve for our OH minus concentration. And so when we take the negative log of that at the end, that will give us POH rather than pH. But easy fix there, just do 14 minus our POH, you've got your pH and you're done. So let's go ahead and walk through this. If you want to just try it though, go ahead and pause here and try it out, and then skip to the end of the lecture and see if you got it right. But if you want me to walk through it, just hang in there and I will. All right, so our first step is to write our reaction of ammonia with water. So there it is. So if we write our reaction of ammonia with water, again, ammonia is just going to pull one of the hydrogens off of water, and we're going to produce hydroxide in solution. Our next step is to use that to make an ice table. Okay, so again, we're going to fill in what we know initially. We have our concentration of our weak base, and then again, we're going to cross out water. We don't need that in there, and then we don't have any of our conjugate acid and our hydroxide. Then we'll go ahead and we'll fill in our change table, so minus X for our reactants, plus X for our products, and then we'll add straight down to get our equilibrium values. Then we can go ahead and fill it into our Kb expression. You're always going to have our products over our reactants. So we're going to fill in our X's over our concentration. Again, because Kb is very, very small, we can use our approximation here, and that gets rid of that minus X, so we'll end up with X squared over 0.5. Then we can go through and we can solve for the value for X. right? So if we multiply both sides by 0.5, we take the square root, we are going to get that X is equal to our concentration of OH minus, which is 3.0 times 10 to the minus 3 molar. So again, when we take the negative log of that, we are getting the POH, not the pH. And again, remember what I was telling you before about checking to make sure it makes sense. If you are finding the pH of a base and you come out with 2.5, that should tell you that's wrong, right? You've done something terribly wrong. That's an acidic pH. And then go back and figure out, oh, I took the negative log of hydroxide. This was actually POH. So I'll just do 14 minus that value, and that will get me my pH. And that's the end of today's lecture. We've covered a lot of ground today. We've talked about how to calculate the pH of a weak acid and use that ICE table, right, that equilibrium to find our pH. And then we talked about strong bases being really similar to strong acids in the way that we calculate their pHs, and also just in the way they behave. And then we talked about finding the pH of a weak base solution, which again is really similar to finding the pH of a weak acid solution because they both form an equilibrium with water. So, we've done a lot of calculating today, but hopefully it's all made sense. I would recommend go and finding your lecture worksheets. There are a ton of practice problems in this chapter. I have made a very, very long lecture worksheet packet for you so that you can get all of the practice you need to feel really confident in doing these problems. So make sure you're getting all of that practice, and if you're getting stuck, please reach out to me and ask for help. You can send me a message and I will be happy to answer any questions you have and walk you through the problems. So get lots of practice. Like I said, hopefully I've said that enough times because I really mean it. You're going to need to know how to do these problems well for the rest of the chapter and for the chapters coming up, okay? We're going to use this to do other cool things like buffer problems and titrations, so you need to be really good at calculating the pHs of these solutions. So, like I said, keep working hard, send me any questions you have, and otherwise, I will see you all next time.